Hi everyone, thanks for having me today. I'm Ben, VP of R&D at Arti.AR. I'm recording from our offices in Tel Aviv, where we work on a cloud-based platform for augmented reality, or AR for short. Today, I'll talk about democratizing AR. I'm passionate about telling stories in AR, and I'd like to touch on why briefly. My talk will include what's needed in the problem space of AR in video, challenges in addressing the problem space. I'll present our platform and the technical challenges we encountered along the way. The three building blocks for great AR video are workflow, content, and AR magic. To allow anyone to create content, we need an AR for video application that is easy to operate and integrate. To enable discovery and creativity, we need abundant content and ways to explore it. To take presentation and convert it to AR is like converting a book to a movie. The visuals are entirely different. The framing, the lighting, the tracking, and everything that makes the AR graphics appear as if they are in the same physical space right next to us. There are several challenges to tackle to democratize AR. One challenge is the lack of simple and affordable tools to generate high-end AR graphics. Mapping the existing overlay design tools, they fall within these categories. 2D only overlays which are not AR, mobile quality AR, and broadcast quality AR. Well, who can use these design tools? Almost anyone can use 2D design tools. Most 3D designers can design AR graphics for mobile tools, but with a significant modification to their workflow. A trained professional AR team can create AR graphics for broadcast quality pipelines. Current broadcast level AR requires expensive hardware and complex solutions that limit setup mobility. AR is hard to execute and requires expertise. We've all seen the AR on the Super Bowl. A lot of money and hard work are invested in broadcast AR solutions, and the broadcast AR system can cost $300,000. Mobile devices are more affordable, but are still limited in graphics capabilities and storytelling tools, and unsuited for studio setup for high-end production pipelines. We store most of our professional content on PCs and laptops, not mobile devices, and there's a large variety of workflows for video content generation. Creators need a rapid, easy workflow, but already rely on multiple expert systems, tools, and formats. When using a laptop or mobile device, we can't rely on the availability of intrinsic camera information in most cases. Poor wireless internet connectivity and weak rendering capabilities reduce the overlay quality of the result. We are all exposed to high-end graphics in movies and games, but due to the lack of middle ground between high-end and mobile devices, things are not that great on live streaming, online videos, and conferencing. Besides the technical challenges, this new medium requires a simple content generation workflow. Everyone can create a slide deck today, and the challenge is enabling non-designers to create AR graphics without 3D design expertise or technical expertise in rendering engines. AR for video is a new medium. There's no shared design language, and there's magic to take care of in an AR composition. For example, you need to place yourself in a suitable space and frame your shot to leave room for your graphics. It would also be nice if you gesture to the 3D object while talking about it. This magic is hard to do. Nobody does that naturally. Creators must understand the medium for AR video overlays, their composition, and their framing. Let me tell you a little about Arti.AR and our approach to tackling these challenges. Arti is a software-only cloud-based platform, allowing non-designers to easily produce professional-looking AR content in any live video. We made an AR platform that is easy to operate and integrate, so you can focus on your presentation instead of relying on supporting AR department. Realizing that content and experience are equally important as the platform and infrastructure, we took a dual-domain approach to democratize AR. One domain is the cloud-based AR and video pipeline. It includes using Unreal Engine hosted in the cloud, computer vision and deep learning algorithms, including tracking, a robust, diverse, and integrative video pipeline. This domain enables broadcast quality AR to become affordable and available with any camera and setting, anywhere, anytime. The second domain is the unique UX and content creation pipeline. It includes AR authoring and presentation UX for non-designers, template designs, third-party design tools, and data sources integration. This domain enables anyone to easily create relevant AR presentations and communicate engaging and memorable content. Research support positive effects on viewers' engagement and memory of their experience. AR content is 70% more memorable and 3 times more engaging than 2D content. Hi, I set up my laptop with Arti to present an AR story. AR is a great tool for telling stories. Our ancestors used to sit around the campfire telling stories, and this is how we can do this today. We can use AR to tell compelling stories. We can talk about this printed circuit board. When you buy this product, please ensure that it suits your power constraints and your space constraints. These are our prices. It's hard to create 3D content. We can project 2D textures on 3D templates. So the creator has an easy workflow, and the viewer gets a 3D experience. Why was this a good video frame for AR? For one, the table serves as an AR playground, or surface to position the graphics on. This simplifies the interaction with the graphics. I added small gestures in my presentation, pointing to and looking at the graphics that were not there. The reflection and shadows are also projected on the surface, which adds to the realism of the scene. So it is important to have high-quality graphics rendering. The usage of templates unlocks creativity where it's difficult to create content. Our solution uses the following process to enable templated use. After a designer creates the concept art, a 3D designer can create 3D models, textures, and animated rigs in any 3D software. By following simple guidelines, Arti-certified designers can use our JSON API to expose data fields in the templated design. After the designer uploads the assets to the platform, the final template can be used inside the platform, where the data fields are exposed for editing to enable customization. Future work in this direction will include automation of this process. We support video as a data field input, including transparent video and screen sharing. Video files are streamed to the rendering engines when the story is played back. Screen sharing requires two-way streaming. Streaming the grabbed input from the client-side web application to the rendering engines, projecting the stream on the graphics, and streaming the graphics back to the application. To follow the simplicity driver, we built Arti, the first AR platform anyone can use. Our user authoring interface design aims for simple content exploration using panels for all AR-related asset browsing. Since our goal is to reach anyone, we enable the use of templated AR designs. This approach unlocks the ability for non-designers to make use of the system with relevant content such as graphs, detailed 2D screens, and layouts composed of multiple 3D graphical elements. The design parameters are kept minimal and straightforward, and content creation and presentation are all within a single screen. The application integrates into the creator's video creation workflow by receiving the video stream from various sources. The application overlays the video and graphics and then streams, records, or relays the composited frames to the other production and video conferencing tools. We don't send the video to the backend. This approach reduces the upload bandwidth and keeps the solution simple to integrate, as all workflow integrations are on the client-side web application. Besides the client-side web application, we utilize Unreal engines to render the graphics. Instead of rendering on the edge computer, we host rendering engines on the cloud. This approach solves the challenges of affordability and limited device capabilities or integration. Rendering the graphics on the back end allows us to reach users that don't have the latest GPU while still delivering great graphics. Utilizing multiple cloud providers helps us increase our availability, reduce costs, and have an affordable solution. We designed a modular architecture that enables flexibility of the video pipeline and the ability to update the presented data in real time. Our current focus is developing our cloud platform, although we can deploy the same services on-prem to support low-latency updates and integrate with third-party video and data systems. We encode the graphics on the rendering engines and stream them peer-to-peer to the application. We developed a WebRTC-based solution that can match video and graphics frames and handle alpha blending for graphics and special effects. We need a stable protocol and low latency, so we devised what to calculate locally on the application and the backend. We send only a minimal set of time and computer vision parameters from the application to the rendering engines without uploading the video stream. While currently the client side is responsible for the frame matching, in future work we'll support video streaming directly to the cloud service and perform the tracking, graphics rendering, and compositing in the backend. The platform will send only the final composition to the end user, enabling simpler workflows. We need everyone to get their specific overlay. so we need an equal number of rendering instances as we have online users. We host a signaling service to negotiate the connection between the application and the cloud-hosted rendering engines. We create a reliable WebRTC session that can handle disconnections and failover switching. To establish the connection, we utilize stun and turn servers to resolve external IP addresses and relay the stream if needed. Once the endpoints establish the connection, the front-end application performs initial Aruko marker detection. It sends the 2D coordinates along with the timing information of the current video frame to the Unreal Engine via WebRTC. The rendering engines perform the tracking calculation to extract 3D marker position and orientation. Then they render a set of 3D elements in the right place and send the rendered frame back to the application for final composition. The application buffers the video frames and matches the correct video frame with the rendered overlay. The result is an accurate positioning of the graphics according to the tracking information, generated at a delay of roughly 200 milliseconds, which is acceptable for the use cases I described. To support rapid UI responses for live video production, we also utilize WebSockets communication for application-level operations, such as transition to the next slide. For the AR story authoring, the application communicates with the backend REST API to manage the stories, edit the slides and 3D elements, and select content and positioning. Let's dive a bit into the tracking solution. We have 3 uses for Aruko marker detection and tracking that enable the AR magic. To extract camera and tracing properties specifically for the focal length. We also use the marker's position and orientation to define the graphics location in real world and where shadows and reflection will render. We track the Aruko marker in real time to follow the camera movement and user interactions with the graphics. However, there are technical challenges in using Aruko marker detection. The main challenges are that the Aruko marker detection results are inconsistent. Consecutive motionless frames can have a slight difference in detection, and these minor differences can change the focal length or 6 degrees of freedom in a way that creates a poor experience. In addition, Aruko detection is sensitive to changes in lighting and doesn't work at all with occlusions. To overcome these challenges, we implemented a sparse optical flow and decision-making algorithms to choose between the results of the Aruko detection and the optical flow. Why can't we somehow mark the corners of Aruko detection and follow them with the sparse optical flow? Even in ideal cases, optical flow accuracy is limited, and the corners that will be marked in the next frame will have sub-pixel deviations that accumulate as more and more frames are analyzed by the algorithm. Those inaccuracies accumulate and result in a drift in the position of the graphics. So why can't we use Aruko detection on each frame? Aruko detection results are inconsistent. Commonly, consecutive static frames have half a pixel distance in detection, and we've seen even larger differences in our use cases. These small changes are translated into a noticeable change in the focal length or 6 degrees of freedom, which can create a poor experience. We developed a POC for intuitive graphics positioning without any physical marker to simplify the workflow further. There are technical challenges when compositing graphics on top of video. Normally, game engines are not set up for AR overlays. In addition, since there is no alpha channel support for WebRTC, one challenge is overcoming a noticeable shimmering artifact on the edge of the graphics on poor connections. This is due to the difference between RGB and alpha channel quantization and the unknown background colors when Unreal Engine renders soft edges. Our solution uses Unreal Engine media capture system to render the graphics frames, including the alpha channel. We transmit the alpha channel and frame time data by increasing the video frame size and encoding the data in RGB pixels. The received image is decoded on the client side to extract the RGB frame, alpha frame, and frame time. The client side plays back a video frame based on the time information, composed with the graphics overlay using the alpha channel. Another challenge is that special effects require special blending functions, like bloom. The bloom effect layer must blend using the add function instead of a linear interpolation between the foreground and the background to get the correct effect. Sending individual effect layers is one solution, but it requires more network bandwidth. In our current solution, we allow the selection of the blending function with future work to be done in this direction. Considering the light direction and properties, we'll refine the frame composition and then do the AR magic, so our future work in this direction includes lighting detection. So in conclusion, we need AR because we can boost memory and engagement in our presentations. Not everyone can be creative with the current solutions. I demonstrated our approach to tackling this problem and some of the challenges we encountered. We are only beginning and want the platform to serve many people and use cases. We are very excited to see where the journey will take us, and I hope I connected you to our vision and where the future of live video lies. Thank you for watching.